Part 3 of the heterocyclic compounds. In this part, let us see the reactivity of pyrrole. Pyrrole is more reactive than furan, thiophene, and benzene due to high nuclear pi electron density. The reason of its more reactiveness is high nuclear pi electron density. The increasing order of their reactivity is benzene is less reactive than thiophene, and thiophene is less reactive than furon, and furon is less reactive than pyrrole. So pyrrole is most reactive among these molecules. It has amphoteric nature. Amphoteric means acidic as well as basic. So both the natures are existing in single molecule, or both acidic and basic properties are shown by pyrrole molecule. It behaves as very weak base due to involvement of lone pair of electron on nitrogen in formation of aromatic sex state. If the lone pairs on nitrogen, if they are freely available, then pyrrole may behave as strong base, but these are not freely available. These are involved in aromatic sex state. That means aromatic sex state means group of those six electrons which are engaged in showing aromaticity, or they are engaged in delocalization, or they form pi electron density over the molecule. So as these electrons are engaged in aromaticity, they are less available to show basic characters. It also behaves as weak acid due to greater stabilization of pyrrole anion. When this proton is removed, H plus, we will get anion, and that anion is pyrrole anion is well stabilized. Hence, it also it behaves as a weak acid. Pyrrole is more reactive than benzene towards electrophile. This is because in pyrrole, aromatic sex stage is spread over 5 atoms only, while in benzene it is spread over 6 atoms. Aromatic sex statement, that means 6 electrons are spread over 6 atoms in carbon, but here in pyrrole 6 electrons are spread over 5 carbons. So more pi electron density. Does pyrrole behave like highly activated benzene systems such as phenol or aniline? Then let us talk about basic characters. Pyrrole is extremely weak base than secondary amine. In nitrogen compound, the lone pair of electron is responsible for usual basicity. That means lone pairs on nitrogen, these are responsible for showing basic characters. But these electrons are not freely available in pyrrole, so pyrrole is weak base. These are not freely available, that means these are engaged or they are involved in aromaticity. In pyrrole, the lone pair of electron on nitrogen is involved in the formation of aromatic sextate. Hence, it is not available for sharing with acids. So, it is weak base. According to resonance concept, nitrogen atom in the resonance is positively charged. Hence, it has least tendency to receive proton from acids. That means if these electrons are involved in aromatic revolution or aromatic delocalization, less amount of electron cloud is available with nitrogen. So it cannot accept the H plus from acid. That means it will not behave as a strong base. So it is a weak base. And pyrrole is weak base. Its Kb value is pKb value 2.5 into 10 raised to minus 14. It is 2.5 into 10 raised to minus 14. Then secondary amines are pyridine. However, it is this is the resonance hybrid of pyrrole. It's slowly dissolved in dilute acids. The protonation in acid solution takes place at position 2 or 3, followed by polymerization at the expense of aromatic characters. If at all protonation occurs either at 2 position or 3 position. But if protonation occurs on either of these two sides, it will lose aromatic character. Loss of aromaticity will take place. So this is not aromatic. This one is aromatic. As delocalization breaks, conjugation breaks here, and delocalization is not possible. When we think about acidic characters of pyrrole, pyrrole is weak acid, both weak acid and weak base. So pyrrole is weak acid and pKa value is equals to the Ka value is equals to 10 raised to minus 15. The acidic character of pyrrole is due to the following reasons. And reason number one, relatively easy dissociation of proton attached to nitrogen. Deprotonation or dissociation takes place easily. Pyrrole is a resonance hybrid of various contributing structures having positive charge at nitrogen. This helps in release of proton. Also, lone pair of electron on nitrogen is contributed towards formation of aromatic sextate. Hence, hydrogen is less firmly held by nitrogen. As these electrons are involved in delocalization or these are involved in aromatic sextate, this nitrogen hydrogen bond is very weak and it can be easily detached. The hydrogen can be lost by proton and deprotonation takes place to give rise to pyrrole anion. And this pyrrole anion is well stabilized. The greater stability of pyrrole anion formed after deprotonation as compared to pyrrole. As this pyrrole anion is stable as compared with pyrrole, the stable species formed easily, so deprotonation takes place easily. So it behaves as acid. And resonance stabilization of pyrrole anion can be shown by this diagram. The negative charge can be delocalized here and double bond formation takes place. This double bond will be shifted and converted into negative charge. Then negative charge into double bond and double bond into negative charge. Then negative charge into double bond and double bond into negative charge or lone pair. And hence this delocalization goes on. Remember, whenever we delocalize double bond or lone pair, follow in the same direction. Never reverse the direction. Either you can delocalize in clockwise direction or anti-clockwise direction. But if you started as anti-clockwise, then till end follow the same direction and continue up till as you get the identical initial molecule. If this is 1, then if we delocalize this, we will get here double bond and here negative charge and here this. Then this will be the final structure and we will get the initial structure. So the weakly acidic nature of pyrrole is explained by the following reaction. Pyrrole on treatment with solid potassium hydroxide forms alkali metal salt. This pyrrole react with KOH to form alkali metal salt, potassium salt of pyrrole, pyrrole. This also shows the acidic nature as pyrrole reacts with base, that means it is acidic in nature. Pyrrole on reaction with Grignard reagent forms salt like N magnesium halide. So pyrrole reacts with methyl magnesium bromide, that is Grignard reagent, to form N magnesium bromide. Salt pyrrole N magnesium bromide is formed. Here, this hydrogen is removed and it is attached with this part. It will give CH4, and this positive part is present as counter ion with nitrogen, negative nitrogen. These reactions show the acidic characters of pyrrole. Then electrophilic substitution with general mechanism. Pyrrole is an excessive pyrrole is an pi excessive heterocycle. That is, more pi electron density is there. That is, pi electron density is greater on its carbon atom than benzene. It undergoes electrophilic substitution reaction rather than addition reaction. Pyrrole is more reactive than benzene and in fact resembles with most reactive benzene derivatives such as aniline and phenol. Pyrrole prefers to undergo electrophilic substitution reaction because it is electron rich. It has cloud of 6 pi electrons above and below the plane of a ring, that is aromatic sextate, and this aromatic sextate is involved or revolving on 5 atoms. So the orientation of electrophilic substitution reaction can be explained by this diagram. And electrophilic substitution, if we draw attack at 2 position and attack at 3 position, so 1, 2 position and 3 position. If attack takes place at position number 2, these are the 3 resonating structures that we can draw. If attack takes place as like this, here it forms and the positive charge will be at 3 position, and this bond shifting and charge shifting will give rise to these 3 resonating structures. But attack at position 3, if attack takes place as like this, then positive charge will be at 2 position as like this, and shifting of bonds and charge, that is delocalization or resonance stabilization, will give rise to 2 resonating structures. Only 2 resonating structures are formed. 2. Attack at 2 position gives 3 resonating structures, and attack at 3 position gives 2 resonating structures. And we know that as number of resonating structures is directly proportional to stability of that attack or probability of that attack. Probability. And as this resonance stabilization after attack at 2 position is greater as compared with resonance stabilization after attack at 3 position, so attack is more preferable at 2 position. And in final step, after deprotonation or removal of hydrogen as a proton, we get substituted pyrrole. And attack at 2 position initially will not be allowed if three if the two second positions are blocked. If pyrrole is there and here one substitution is there, here also one substitution is there, then attack at position 3 will take place. This is due to greater stabilization of intermediate carbocation formed during the attack of electrophile at position 2, 3 resonating structures, as compared with the intermediate carbanion formed during the attack of electrophile at 3 position 2 resonating structures. But when position 2 and 5 are blocked, then electrophilic substitution takes place at position number 3. Pyrrole, similar to more reactive benzene derivative like phenol and aniline, undergoes electrophilic substitution reaction. Like phenol, it undergoes Kolbe-Smith, Riemann-Tiemann coupling. These are the electrophilic substitution reactions. All reactions are shown by pyrrole also. So general mechanism of electrophilic substitution reaction. General reaction is pyrrole react with electrophile and attack at 2 position takes place. So this 2 substituted pyrrole is formed. This is the general mechanism of electrophilic substitution reaction. And in steps, we can write attack of electrophile, which is a slow step to form sigma complex. And in the second step, this sigma complex removes hydrogen as a proton to give 2 substituted pyrrole. In the first step, the pyrrole is aromatic. When attack of electrophile on that pyrrole takes place and there is formation of sigma complex, this is non-aromatic sigma complex. To regain its aromatic character, this non-aromatic sigma complex removes hydrogen as a proton or eliminates hydrogen as a proton from the carbon where electrophile is attached, and it regains its aromaticity. So this one is final product is aromatic and we get 2 substituted pyrrole. This is the general mechanistic steps of electrophilic substitution of pyrrole. Thank you.